Introduction to Taylor Polynomials. We're going to start by doing a little bit of a graphical analysis. What function does this look like? Well, since it passes through the origin and it's linear, it looks a lot like the function y equals x. It turns out that that last graph was actually really zoomed in. So if we zoom out, what function does this look like after all? Well, it looks like a cubic polynomial now. Since the right side's end behavior is going down to negative infinity and the left side's end behavior is going up to positive infinity, this cubic polynomial will need a negative leading coefficient. So it's going to be something like negative ax cubed plus maybe some bx squared plus cx plus d, where d is of course 0 because this passes through the origin. So some variation of a cubic polynomial. Well, it turns out that that last graph was actually really zoomed in as well. And if we zoom out further, what actual function is shown? Well, we have the sine function. So we were zoomed in originally and it looked like y equals x, and then we zoomed out a little bit and it looked like a cubic, but it turns out that all along we had the function y equals sine x. So what does that mean? What is the takeaway? Well, we already know how to find linear approximations for a function, but what the graph above suggests is that there might be a cubic function that does a better job of modeling the sine function on a wider interval. So from our first calculus course, we learned about using a line to approximate a function, but it looks like here that a cubic polynomial would do an even better job of approximating the function. So we're going to go ahead and dive into that conversation. In this graph on the left, here we have the sine function, and we have the linear approximation to the sine function at 0 drawn. And then we also have a cubic function drawn that passes through the origin, and that cubic function is x minus x to the third. So what I want you to start to observe is that near 0, these three functions appear to be the same function. But as we go further away from 0 on both sides, the two different approximations, the line and the cubic polynomial, stop being good approximations. There's obviously a large error as we move away from the origin. It stops being really close to the y values of the sine function. Well, if you look over here on the graph to the right, we still have the sine function and we have the line y equals x, our tangent line approximation. And we still have a cubic polynomial, but we've slightly tweaked the coefficient in front of x cubed. So now we have x minus 1 over 6x to the third. And you can see that now that cubic polynomial is really close to the sine function as I get further away from 0. But the line really starts having some serious error. But the polynomial is pretty good. Just by changing this coefficient, I have a better and better approximation for values on the sine function, but using this nice polynomial. Alright, so let's continue to look at the sine graph, but we threw out the line y equals x because that was pretty terrible once I got further away from 0. So let's take a look at sine x. Let's take a look at that cubic polynomial, x minus 1/6 x to the third. And then we're also going to take a look at now an even higher degree polynomial. So we still have x minus 1/6 x to the third, but we're adding on an additional term that makes it a quintic polynomial, 1 over 120 x to the fifth. And so I can see that that function there is an even better approximation as I get further and further away from the origin 0. So the cubic was pretty good up till a certain point, but the quintic is even better. It goes even further, but it does start to give us some error the further away we go from the origin. So what we can now do is think about, well, maybe adding on an additional term and making it a higher degree polynomial will be an even better approximation. And it turns out that that is true. So here we have a degree 7 polynomial, and that's going to give us an even better approximation the further that we go out. It turns out that these coefficients and these exponents, they aren't random. So it turns out that sine x is approximately x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, and this alternating pattern continues of the sine and the exponents and the factorials to have this general form. So here we have the negative 1 to the n means they alternate. X to the 2n plus 1 means that we're going to have odd powers of x, and we're going to divide by those odd powers and have each be a factorial. And this is going to be true for all values of x on the interval from negative infinity to infinity. So the sine function can be approximated by polynomials, which is a great thing because a sine function is a transcendental function. It's hard to plug values into sine that aren't just really nice radian values like pi over 3. But we can plug any number into a polynomial, and that work is a lot easier. So we're soon going to see how this polynomial was determined using derivatives. Before we go any further, we're going to emphasize the main idea. We are interested in these special polynomials, Taylor polynomials, because they give us a way to approximate transcendental functions that we cannot directly evaluate. They also allow us to work with transcendental functions in many other wider applications. Let's look ahead to a future application. In this example, we want to recall that by L'Hopital's rule, the limit as x approaches 0 of sine x over x is equal to 1. We want to use a Taylor polynomial to reach the same conclusion. We will have to approximate sine x, but as we noticed earlier, near 0, which is what our limit is approaching, our polynomials matched the sine function exactly. We will make this more exact in the future. So let's start by approximating f of x equals sine x over x with a polynomial. Well, sine x was approximately x minus 1 over 6 x to the third plus 1 over 120 x to the fifth. Sine x over x then can be approximated by taking the polynomial and dividing by x. Simplifying, x over x becomes 1. X to the third over x is x squared with the same coefficient, and x to the fifth over x is x to the fourth with the same coefficient. So now, if we want to evaluate the limit as x approaches 0 of sine x over x, we can approximate the limit as x approaches 0 of the polynomial representation. So 1 minus 1 over 6 x squared plus 1 over 120 x to the fourth. Evaluating this limit is nice because substituting in 0 for x means that we only have the constant term 1 remaining. So this was an example of an application for Taylor polynomials to evaluate limits. Now we're ready to define an nth Taylor polynomial. The nth Taylor polynomial of some function f of x centered at x equals a is the polynomial t sub n of x is equal to f of a plus f prime of a over 1 factorial x minus a, and this is to the first power, plus f double prime of a over 2 factorial times x minus a squared, plus the third derivative of f at a over 3 factorial x minus a to the third, plus, and this would go all the way up to the nth derivative at a over n factorial times x minus a to the n. So we want to start to notice the pattern here that if we're taking the first derivative, that corresponds to 1 factorial, and an exponent of 1 with the term x minus a. If I have a second derivative, that goes over 2 factorial, and then I have x minus a squared. And this repeats if we have a third derivative, we divide by 3 factorial, x minus a to the third, all the way up till our power of n if we wanted a degree n polynomial. So we can write this in condensed form as a series. So this series would go from I equals 0 to n, and we're taking the ith derivative at a over I factorial x minus a to the I. So we'd start at 0 because that's going to give us this first term, just f of a, and we're going to end at n, which is going to give us our nth term. Where all of these higher derivatives, they have to exist in some interval around x equals a, because that is the center. We say that n is the order of the Taylor polynomial, and if a is 0, which is the center, so if the center is 0, then t sub n of x is called the nth Maclaurin polynomial. Here are a few expanded Taylor polynomials centered at x equals a. The Taylor polynomial of order 0 is just f of a. The Taylor polynomial of order 1, or the first order Taylor polynomial, is f of a plus f prime of a times x minus a. The second order Taylor polynomial is f of a plus f prime of a x minus a plus f double prime of a over 2 factorial x minus a squared. And if we look at a third order Taylor polynomial, we have all the same first 3 terms plus the third derivative of f at a over 3 factorial x minus a to the third. So what I want you to notice is that a first order Taylor polynomial is really just the linear approximation, or the tangent line at x equals a. So we called that the linearization, the linear approximation or tangent line. So that's f of a plus f prime of a times x minus a. So really this is just the point slope form of a line. So this is like my slope m, and this is x minus x1, and this value is our y1 value. So the Taylor polynomial of order 1, or the first order Taylor polynomial, is really just a linear approximation, which we use to approximate functions. So now we're just extending that idea by creating a higher degree polynomial called a Taylor polynomial. So in this introductory section on Taylor polynomials, let's go ahead and stop to think about observations so far about Taylor polynomials. First, they match the function perfectly at the center x equals a. They lose accuracy as we move away from the center, but they gain accuracy as we add more terms to the polynomial. Let's end with some motivating questions to fuel what we're going to do going forward. Number 1, is there a systematic way to come up with the coefficients of a Taylor polynomial for a given function? Number 2, how good are Taylor polynomials? What is the error between a Taylor polynomial and the original function? Number 3, can we extend the interval on which the Taylor polynomial is a good fit? And finally, if we use infinitely many terms, can we match the function exactly? Building a Taylor polynomial. To build a Taylor polynomial, we're going to need the formula. So the nth Taylor polynomial of f of x centered at x equals a is the polynomial t sub n of x is equal to f of a plus f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial x minus a to the second power and so on all the way up to the nth derivative at a over n factorial times x minus a to the n. So this is the formula that we're going to be using to build our Taylor polynomial. And we want to remind ourselves that the degree of a Taylor polynomial, or a polynomial in general, is the highest exponent of x in the polynomial. The order n of a Taylor polynomial is the order of the highest derivative used to compute the polynomial. So often these will be the same, but sometimes these will just be slightly different, the degree versus the order. In this example, we're told a function f has the following properties. F of 1 equals 2, f prime of 1 equals negative 1, f double prime of 1 is equal to 1/2, and f triple prime of 1 is equal to 3. Find the second and third order Taylor polynomials for f centered at x equals 1, which is the better approximation for f of x near x equals 1 and y. So let's start by finding the second order Taylor polynomial. That means that the highest derivative we're going to use is the second derivative. So we'll start by saying that t sub 2 of x is equal to, I'll write it in general first. So the formula says that we're going to have f of a, f of the center, so that's f of 1, plus f prime of 1, and then it's over 1 factorial times x minus 1 to the first power, plus f double prime of 1 over 2 factorial times x minus 1 to the second power. So this is my second order Taylor polynomial, but I have to substitute in these values for f of 1, f prime of 1, and f double prime of 1. So f of 1 we were given is 2, so we have 2 plus, well, f prime of 1 was negative 1, and 1 factorial is 1, so we simply have minus x minus 1 to the first power, and then we have plus the second derivative at 1, which is 1/2, so I have 1/2, but over 2 factorial, and 2 factorial is 2 times 1, which is just 2, times x minus 1 squared. So what I end up with is 2 minus x minus 1 plus 1 over 4 x minus 1 squared. So this is the second order Taylor polynomial because the highest derivative I used was a second derivative. And it happens that this is also a degree 2 polynomial because the highest exponent of x I would end up with is an x squared. So now let's go ahead and find the third order Taylor polynomial. And that means that the highest derivative that we're going to use is the third derivative at 1. So what we're really doing is we're just going to go one additional term out. So I can go ahead and say this is t sub 2 of x, and that's part of my answer. But finding t sub 3 of x is simply going out one additional term here. So I'm going to go ahead and say that t sub 3 of x is equal to, I'm going to keep these first 3 pieces, so 2 minus x minus 1 plus 1/4 x minus 1 squared, but then the next one is going to end up looking like plus the third derivative over 3 factorial. So the third derivative, f triple prime of 1 over 3 factorial times x minus 1 to the third power. So I'm writing it generically first, but now I need to substitute in this value, which was just 3. So we're going to have this term is 3 over 3 factorial times x minus 1 to the third, and then I continue with all the remaining pieces. Those are still there. And then I can simplify the last term now to be, well, 3 factorial is 3 times 2 times 1, which is 6. So 3 over 6 is 1/2. So I have 1/2 x minus 1 cubed. So this is my third order Taylor polynomial, or t sub 3 of x. So it's going out and just finding that one additional term that's created using the third derivative. And then finally, we're going to answer the question, which is the better approximation for the function f near x equals 1 and y? Well, we know that adding on additional terms gives us a better approximation of the function. So the one that's going to be the better approximation near 1 is t3, because the more terms that we add to the polynomial, the better. To formalize that, we would say t sub 3 of x is a better approximation than t sub 2 of x because it has more terms. In this example, we want to find the third order Taylor polynomial for f of x equals the square root of x near x equals 1. So since we need the third order Taylor polynomial, we're going to need the third derivative of our function, the square root of x, and then we're going to have to substitute in x equals 1 to each of those derivatives. So we'll start by writing f of x is x to the 1/2, so its derivative is 1/2 x to the negative 1/2. The second derivative is going to be negative 1/4 x to the negative 3/2. And the third derivative of x is going to be positive 3/8 x to the negative 5/2. So we're just applying the power rule. Now we need f of a, f prime of a, f double prime of a. And our a value, our center, is 1. So we're going to have f of 1 is just the square root of 1, which is 1. And then here, if I plug in 1 to the negative 1/2, it will bring it to the bottom, but it's still just going to be a 1. So we're going to have just the 1/2. So f prime of 1 is a half. F double prime of 1 is just going to be negative 1/4 for the same reason, substituting in 1. It's just going to give us 1, so we're going to have negative 1/4 there. And the third derivative at 1 is positive 3/8. Now we can go ahead and start building our third order Taylor polynomial. So t sub 3 of x, in general, I'll write out, well, we were looking for f of 1 plus f prime of 1 over 1 factorial times x minus a being 1 to the first, plus the second derivative at 1 over 2 factorial x minus 1 squared, and the third derivative at 1 over 3 factorial times x minus 1 to the third. So this is the general formula, and then we substitute in the values that we found over here as scratch work. So f of 1 was 1, plus f prime of 1 was a half, so I get a half over 1 factorial, that's just a half, times x minus 1, plus, now we have f double prime of 1, which was negative 1/4, and then over 2 factorial, which is 2, times x minus 1 squared, plus f triple prime of 1, that was 3/8, so 3/8 divided by 3 factorial, which is 6, times x minus 1 cubed. And now it's just a matter of really simplifying these two coefficients. So the other two parts are fine, so we have 1 plus 1/2 times x minus 1, and then this is going to be minus, so here 1/4 divided by 2 is like 1/4 times 1/2, so we're going to have minus 1/8 x minus 1 squared. And then here, 3/8 over 6, well that's 3/8 times, instead of dividing by 6 over 1, it's multiplying by 1 over 6. And here we can reduce, so we get 1 over 16. 1 over 16 x minus 1 to the third power. So this is my third order Taylor polynomial for f of x equals the square root of x near x equals 1. And just to tie it back to what we've been talking about, what was the point of doing this? Well, the square root of x is a transcendental function. So if I were to try to evaluate like the square root of 2, that's typically something I would plug into my calculator to find. But now this is an approximation for the square root function near 1. Well, 2 isn't super close to 1, but it's close enough. We could use this polynomial to approximate the value of the square root of 2 by simply plugging 2 into each x. So that's, well, again, what we're doing when we're finding these Taylor polynomials. The third order, because we use the third derivative, this also happens to be a degree 3 polynomial. In this example, we want to find the 6th degree Taylor polynomial for f of x equals cosine x near x equals 0. We're trying to find the 6th degree Taylor polynomial, so we are going to go up to using the 6th derivative here. At least, we want to make sure that we end up with the 6th degree Taylor polynomial. So we'll take 6 derivatives. So we have f of x is cosine x. The derivative of cosine x is negative sine x. The second derivative of cosine x is going to give me a negative cosine x. The third derivative is going to give me a positive sine x. The fourth derivative, and we stop using prime notation, is going to give me cosine x. The fifth derivative is going to give me negative sine x because we've now gone in a circle. And the sixth derivative is going to give me negative cosine x. Well, now we want to evaluate each of these at 0. So we're looking at f of 0, cosine of 0 is 1. F prime of 0, sine of 0 is 0. F double prime of 0, if I plug in 0 to cosine, I get 1, but there's a negative on the outside, so I get negative 1. The third derivative at 0, sine of 0 is 0. The fourth derivative at 0, cosine of 0 gets me back to 1. Hopefully we can see this pattern that's happening here. So we have now the fifth derivative at 0 is 0. And the sixth derivative at 0 is negative 1. So we have, again, cosine of 0 is 1 and a negative on the outside. So from here, we can start to build our Taylor polynomial. Alright, so we're going to go ahead and say that t sub 6 of x is going to be f of a. Well, f of 0 is 1, so I'm just going to start substituting in automatically. And then plus, so here we're going to have 0 over 1 factorial, and then x minus 0 to the first power. So that term's actually going to disappear. Plus, now we're going to have the second derivative at 0, so that's negative 1 over 2 factorial, and then we're going to have x. It's going to be x minus 0 every time, but that's obviously just x, so I'm going to leave this as just x squared. Then I'm going to have plus the third derivative at 0 was 0, so we'd have 0 over 3 factorial, and then x cubed, but that's just going to give us 0. So 0 over 3 factorial is 0, so that term is gone. And then we'll have plus the fourth derivative at 0 was 1, so we'll have 1 over 4 factorial, and then x minus 0 to the fourth. And then, you may have guessed, the fifth derivative at 0 is 0, so that term is actually going to be gone as well. 0 over 5 factorial x to the fifth, so that term is gone. And then here we're going to have the sixth derivative at 0 was negative 1, so we have negative 1 over 6 factorial, x minus 0 to the sixth. Alright, so we can see, what do we have left? We only have left the 1 and then all of the terms with even degrees. So we're going to have 1 minus 1 over 2 factorial is 2, so we have 1/2 x squared, plus, now we have 1 over 4 factorial. So 4 times 3 times 2 times 1 is going to give me 24. So I'm going to have plus 1 over 24 x to the 4th. And then we lose the odd degree, so we have minus 1 over, well, 6 factorial is a pretty big value already because factorials grow really fast. It's going to be 720. So we have 720 x to the 6th. So we do have, after using 6 derivatives, a degree 6 Taylor polynomial for cosine x near x equals 0. And so one of the things that I want you to just observe here is if I substitute in 0, well, all of these terms here are going to go away, and we know cosine of 0 is 1. So we can start to see that we have built a polynomial that does exactly represent cosine at 0 and then approximately represent cosine near 0. The other thing I would want you to notice is that since cosine is an even function, its polynomial representation should also be an even function, and we can see that it's consistent of terms that all have even degrees. So just some of the things to maybe notice about the polynomial representation or polynomial approximation.